seminar session. My name is Supratim. I am going to present matrix sketching with guarantees. So first of all, what is sketching? Sketching is nothing but the approximate representation of data that you have. Okay, and there are many scenarios where we continuously get data from different sources, such as machines, network traffic, logs, etc. And it is quite important to detect if there is any anomaly in the data very quickly and as well as accurately. So for that, so that we can prevent further issues such as like machine failures or intrusion detection, something like that. So so to understand that how matrix sketching comes into the play, let us look at one example in data anomaly detection. So so in here we have a streaming data as a matrix of dimension, let's say n cross d, where these rows will tell us the timestamp, and the columns are the features. We can take it as like sensors, maybe, as an example. And in here we are getting data as one row at a time. So the stream is over rows. Let's say we are at some ith row. What our algorithm will do is that so at the ith row we would already have kept an approximate representation of non-anomalous data. Till now we have seen until I minus 1th row. And we are going to call this matrix as the sketch matrix. So so what it will do, whenever we see a new row, our algorithm will query it to our approximate representation of this non-anomalous data, and it will query that whether this new row is a good data or a bad data. If it is a good data, then we will update our sketch over here, and or else if it is a bad data, we will just discard it. So that is what this matrix sketching will help us. So here this sketch so here this sketch matrix will have a dimension of L cross D. So certainly we don't have to compute the operation over this N cross D. So it will take less time to answer our query. Okay. So I hope this is clear, the motivation why we need this matrix sketching. So now before going into the matrix sketching, let us see a simpler version of it, that is frequent items. So in here the problem statement is that we have a universe of size m, and from this universe we are getting stream of data as a1, a2 up to an, and in here we want to answer the query that how many times a particular data has appeared. So one of the very naive solution could be that we simply keep m counters for each item, and whenever we see an item in our stream, we will go to the particular counter of that item and we will increment by 1. So certainly it will give us exact frequency, but also it will cost us a lot of space, that is order of m. And in here it may be the case that m is quite large. So we don't want that. So maybe if our motivation is not to know the exact frequency of all the items, rather let us get to know the frequency of top L items in the stream that we have. So so in that problem, Misra-Gries has given the algorithm for this in the year 1982. So the algorithm goes like this, that instead of m counters, in here we will have L counters, and what we will do is that whenever we see a new item AI, if the item is present in the list, we will increment its particular counter by 1. If the item is not present in the list and the list has less than L item, we are going to add the item in the list and we will set its counter to 1. Or at the final condition would be the item is not present and the list is full. In that case, yeah.
That is not aligned correctly.
No, it is aligned correctly. It is. So like there can be 3 cases. One case is that AI is present in the list, then we will simply increment its GI. If AI is not present and the list length is less than L, then it means that we have a space to retain the counter of one more item. So then we will insert that item and we will set the count to 1. And the last case could be that AI is not present in the list and our list is full. Then what we will do, we will simply decrement the counter of all the items present in the list by 1, and then we will check that if there is any item whose count has become 0, we will remove that item so that we can make space for the other streaming data that we are getting. Okay. So to understand it more clearly, let us see an example. So let's say this is one of the timestamp where we have got an item AI, and in here AI is present in the list. So what we will do, we will simply add it to our counter. Now so we are just incrementing the counter values. So now if the item is not present and the list is not equal to L, so in here we will simply add this item over here and we will set the count value to 1. That is what we are doing here. And then the other case that I told you, the final case is that when the item is not present in the list as well as the list is full, then we will simply decrement this count value of every counter from the list. So that is what is happening over here. And this is what we will be keep on doing until the end of the stream. Okay. So now if you want to query about any particular item, we just query and we return the last count that we had. So this algorithm, so it certainly uses L counters. So it will take order of L space, but it will give you an approximate frequency. It will not give you the exact frequency because we are deleting count values by because of some situations. Okay, so your question is whether L is constant or not. So in here L depends on the approximation that we are willing to take care of. So like if we are interested that the approximate frequency Gj lies between Fi to some Fi minus n by L, so that is where the L comes into play. So I will show you the proof of this. So this algorithm returns the frequency Gi, which is between exact frequency Fi to Fi minus n by L plus 1. So in this algorithm, one thing you can note for sure is that this Gi would be less than or equal to Fi, because every time we are getting an item, we are only incrementing its count by 1. And there are certain scenarios where we are deleting its count. So certainly Gi cannot be greater than Fi. At max it can be equal to Fi or it can be less than Fi. So Gi is less than Fi, that is for sure. Another thing to note is that the Gi is at least Fi minus n over L plus 1. This is because every time when we delete and every time when we are doing this deletion operation, we are removing like L items from the counter as well as the item itself. We are not keeping count of these things. in our sketch. So, so every deletion is giving us is removing L items as well as itself. So like L plus 1 items are not being counted in our sketch, and there are total n many number of streams, n length stream is there. So there cannot be more than n over L plus 1 deletions, because or else we would have run out of streams, and it is over the whole stream from 1 to n, whatever we are seeing it. So by combining these two, we see that Gi can lie between Fi and the upper bound Fi minus. So now we can also see this as a matrix version. So so the matrix version would be that instead of items, we are getting one column at a time, and it is like that that the columns of this this data stream would be coming from this standard vectors E1 to EM. So like if we get AJ as a stream at the as the ith stream, then our actual matrix A will have ith column will have EJ as the standard vector. So the standard vector is representing that which item has come in our stream. Okay. So now if you want to say that what is the frequency of some particular item EJ, we can simply compute this EJ transpose A. This will actually tell us that over all the columns, wherever we have got this jth row to be non-zero, that is what it will add up to. But then over here we have to keep this whole stream with us to tell about the frequency of this particular item. So that is not what our aim is. Our aim would be to build a smaller sketch matrix B, so that if we query the same thing over our sketch matrix B, then the result that we get will not be too far. So like if you see like we see in the Misra-Gries algorithm, our exact frequency, that is our EJ times A minus the approximate frequency, was lying was between n by L. So over here our n would be the Frobenius norm of A, because A is the matrix of all the columns that we are getting in the stream, and every column has only one non-zero entry because it is a standard vector. So standard vector is that ith standard vector is nothing but all 0 except the ith row, that will be 1. So Frobenius norm will be certainly n over here. So in that way we can represent this frequent item into this matrix version as well. So now keeping this in mind, we will see the problem of frequent direction, that is matrix sketching. So in matrix sketching, the problem statement is that we, sorry.
If we use the previous one, then the transpose will just come in the other side. So here you are assuming that the column.
Yes.
Otherwise it just
Yes, or else like here I had considered rows coming as a stream.
If it is row, then just A.
Yes, A into EJ, and it will be. So now keeping that in mind, let's look at the matrix sketching problem. So in here we are given a matrix of streaming matrix of dimension n cross m, and we want to keep a sketch matrix of dimension L cross m. Over here the streaming model is same as that we had earlier, and here we are getting one column at a time. So the intuition behind this matrix sketching is that we are going to preserve L orthogonal vectors in our sketch matrix that that actually approximates good, so like that actually give us a good approximation to the basis of the actual data that we have, that is the A matrix. Okay, and 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 in frequent items we had this operation called deletion. Over there, whenever we are getting an item which is not present and the list was full, we were deleting one from its counter. So in here, instead of that, we will shrink every orthogonal vectors by same amount. This is what our shrink operation would be in matrix sketching. So so let us look at the algorithm over here. Okay, so so here we will fix L, and we would be getting this A matrix one column at a time, and the result we will give you a B matrix, which will be a good approximation to our actual data. So initially we set B to all zeros, and now whenever we get a new column, we insert AI into one of the zero column of B. Now if there is no zero columns present in the B, then we do SVD of B, and we only retain the orthogonal columns of B along with its singular value. And then what we do, we set a delta I to be the median singular value of the SVD, and this delta I will tell us that that how much shrink we have to do in our matrix sketching method. So so like after that, we redefine these singular values as just by deleting every singular value by delta I. That is what we are doing. If the value goes below 0, we set it to 0, because we are keeping the median singular value as our shrink, our amount of shrink that we are going to do. So there will be certain singular values whose after subtracting it will go less than 0. So we will set them as 0. So in a way we are nullifying L by 2 number of orthogonal vectors in our sketch matrix, and this would be our new sketch matrix that we have, and we will keep on repeating it until the end of the stream. So to understand it more clearly, let's look at one example. So so at some I minus 1th time, let's say the sketch matrix looks like this. Okay, now when we get a new column in our streaming matrix, we simply add it to an empty column, and we keep on doing it until the sketch matrix is full. Whenever it is full, we find the SVD of it, and we only retain these orthogonal columns and the singular values. So so in here you can see that the orthogonal vectors are decreasing magnitude order. Okay, so so now what we do is that we so this would be our sketch matrix. Now what we do is that we set the median singular value as delta I, and we are going to nullify this smaller magnitude order of the orthogonal vectors. So that is what we would be doing, and then we will keep and then again when we get a new this streaming column, we will add it to B over here, and we will keep on doing it continuously. So so at the end of the stream, what we will do, we will claim that the A transpose A minus B transpose B, that is the covariance error, will be bounded by Frobenius norm of A over L. So this is what we had seen in the Misra-Gries, the matrix version of the Misra-Gries, if you remember. So in here I have considered X to be the eigenvector of the highest eigenvalue of A transpose A minus B transpose B, So so in that way I am getting the highest difference value of it. So so now if we simply see it,
So if X is such, then that quantity is that. A transpose A minus B transpose.
yes, yeah, so in here A transpose A minus B transpose B's two norm we are talking about. So so if we consider X to be the highest eigenvalue, sorry, highest eigenvector, if we consider X to be the eigenvector of the highest eigenvalue of A transpose A minus B transpose B, then it turns out to be these two are same, because the two norm of any matrix A is defined as supremum of X in RD. If you write norm of AX times, yeah, yes, 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 and here X is not equal to 0. So in here it turns out that X what we get is that eigenvector of the maximum eigenvalue that we had of A. So so that is why this this turns out to be equal to this when X is the eigenvector of the highest eigenvalue. So now if you remember, we had a CI matrix in our algorithm. So so that CI matrix was nothing but the sketch matrix until BI time plus the ith stream that we had seen. So so in here what we have is that the uh, sketch until BI minus 1 plus the ith column that we have seen. Combining these two, we get CI, and this BI comes from top. So now this CIX minus BIX will be less than or equal to CI transpose C minus BI transpose B. This is because here X was the eigenvector of the highest eigenvalue corresponding to A transpose A minus B transpose B. So so like it is not the supremum of what we are defining over here. So this value would be greater than or equal to our actual what we had over here. So so now what we were doing is that once we had this C matrix, we were doing this shrink operation because our sketch matrix was full. So so because of the shrink operation, every time we are deleting this delta I parameter from every singular values. So now this spectral norm of this Ci transpose Ci minus Bi transpose Bi turns out to be the spectral norm of the diagonal matrix of these two. And then since we were deleting delta I in every time, this will give us sum over all the delta i's that we had deleted in our shrink operation. Is this clear? So now to go ahead and prove this bound, we need to find the Frobenius norm of B. So Frobenius norm of B can also be written as sum over Frobenius norm of Bi minus Bi minus 1. And then we will add Ci and subtract Ci in the above expression. Then we get it as a good form, that Ci minus 1 minus Bi and and the remaining, that is Ci minus Bi. So over here Ci was nothing but Bi minus 1 plus Ai, if you remember, if I go back to the algorithm. Yeah. So so in here what we are doing, so in here we already had this sketch matrix B at the I minus 1th step. Now when we are getting a new column, we are adding it to one of the 0 column of B, and from that we are defining this C matrix. So this C is nothing but Bi plus Ai, right? Bi minus 1 plus Ai. So that is what we are getting over here in the proof. Yeah. So so this Ci minus Bi minus 1, that is the sketch until Bi minus 1, would be nothing but this ith column of A, and the remaining part, Frobenius norm of Ci and Bi, can also be written as trace of Ci transpose Ci. This is because like Frobenius norm of A is nothing but sum over square of all the entries in A, and this we can also write it as trace of A transpose A, because trace of A transpose A will give us sum over all the entries of Aij, where Aij times A transpose Ji. So this is again same. Okay. So that is why we have this Frobenius norm of this to be equal to trace of this. So now simplifying it more, we get this trace is nothing but sum of all the eigenvalues that we have in the matrix. So that is what we have it here, that eigenvalues of Ci minus minus the new eigenvalues that we have got after the shrink operation. So this would be less than or equal to Frobenius norm of complete matrix A minus L by 2 times sum over delta I, because in here what we are doing, that there are at least L by 2 elements whose from which we have actually deleted delta I value from it, and that is what it is. So so if we write it, if we just write it in a more proper way, we can see that sum over delta I can be bounded by 2 times Frobenius norm by L. And now combining both the results that we had in the previous and this one, we get this A transpose A minus B transpose B can be bounded by Frobenius norm by L. Now if we pick L to be 2 over epsilon, it turns out that we can bound it by some epsilon parameter of the Frobenius norm. So now before going into other matrix sketching techniques, let me tell you that whenever we define, whenever we build this matrix, sketches of this matrix, we are more interested into this either covariance error or the projection error. So the covariance error is nothing but it tells that for all x, we are going to bound this ax square minus bx square by some factor, and yeah, this is the covariance error. And projection error is the comparison between this k rank of the sketch matrix that we have built to the k rank of the actual matrix that we have. These two errors we are mostly interested into whenever we build the sketch matrix. So now few other sketching methods are like one is frequent directions. So over here, so to get a covariance error this, we need to set L is equals to k plus 1 by epsilon. So so let me just tell you the algorithm that what they use in the frequent direction. So so in here, instead of setting delta I to be the median of the singular value, here we set delta I to be the last singular value that we have, and the shrink operation is as it is, and we return this sketch matrix to be B times U sigma hat. And there is one more called iterative SVD. In here, we do not change the singular values of the sketch matrix until L minus 1. We only nullify the last direction over here. So this you can relate it to the Misra-Gries that we have seen. No, you cannot relate it, because over there we were again deleting some value of each counter. So so in here we are simply nullifying the last orthogonal vector, and we are keeping rest as it is. So so for iterative SVD, we don't have as such proved covariance error or projection error bound. So other variants could be like fast alpha frequent direction. So so in here the notion is that like the smaller the singular value you have, it is because it may be associated to some noise parameter, and the larger singular values are more from are there because it must have come from signals. So so in here we define a parameter alpha, which actually decides that how much shrink we are going to do in our shrink operation while building the sketch of the matrix. There is one more method called space saving method. So the space saving method is actually motivated by a paper by Metwali, which actually outformed this Misra-Gries algorithm. So so in here the idea is that we don't change the singular values until L minus 2. We nullify the L minus 1th column over here, and in the last column we simply add this delta I parameter to it, and in here delta I is nothing but the L minus ith singular value. And finally there is one more method is compensative frequent direction. Over here, so like till now we have seen that in this frequent directions method we are always deleting some so like in the shrink operation we are always deleting some portion of the orthogonal vectors. So so because of that we end up getting some underestimation of the Frobenius norm of the stream. So just to retain that we don't get underestimation of the stream, we keep a bookkeeping over here, that is capital delta, which actually keeps this how much shrink we are doing in every shrink operation, and at the end of the sketch we simply add it to all the singular values that we have come up of the sketch matrix, and then we re-evaluate this. So these are the references that I have used for this.